Мы начинаем очередное заседание семинара Математического института имени Стеклова. Сегодня у нас доклад профессора Луиджи Аккарди из Римского университета Тор Вергата. Это комбинированное такое у нас получается заседание с занятиями, с работой конференции по квантовой вероятности. Профессор Аккарди один из основателей этой квантовой теории вероятностей. Он говорит по-русски, хорошо говорит по-русски, но вот я не знаю, на каком языке он будет сейчас говорить, видимо, по-английски. Может быть, Луиджи будешь делать иногда комментарии по-русски тоже.
Если вопрос будут,
хорошо,
я, может быть, отвечаю.
Тема его выступления – это ортогональные полиномы, квантовая вероятность, ну, Луиджи скажет точнее. Приятно отметить, что профессор Аккарди получил образование, занимался с академиком Колмогоровым и Гейльфандом здесь у нас в Москве, так что это наш старый друг и коллега. Now I will switch to English. We start our Стеклов Institute seminar, monthly seminar. This time it is combined with the session of the QP, Quantum Probability 34 conference. And we have a pleasure to get the talk by Professor Luigi Accardi from the Roman University Tor Vergata. We know well that Professor Accardi is one of the founders of quantum probability theory. Please.
Thank you very much.
Yes.
Okay. I'm very glad to speak in this circumstance, and especially for giving a talk in this Steklov seminar. I hope that there will be the possibility to have some exchange of ideas on the topic that I will discuss. So I will not go very much into the historical, but I want to try to describe the logic that we are following. I will discuss a very, very traditional field of mathematical analysis, which is the field of orthogonal polynomials. However, we could do some step forward and to give some contribution to this field using new techniques that come from quantum probability. In fact, what I want to prove, and I will try to convince you that the theory of orthogonal polynomial is in fact just the theory, just quantum theory. Jacobi could have invented quantum theory. I will just, of course, a posteriori you reconstruct history in 1,000 ways, but I want to show that in this case, really, the situation was very, very near. So let us try to go at just to fix some terminology. I will, the starting point is a probability measure, but in fact, I only need the restriction of the integral of the probability measure to the polynomial algebra, which I will denote with the P of x, and sometimes simply with P. X I will use now because I want to begin to discuss only the simplest case, because there I can explain the fundamental concept very quickly. Then I will discuss the much more difficult case of multidimensional. But maybe it's easier for people to follow from this. Yeah, they follow. Yeah, and you see, so when I speak of probability, I mean state on the polynomial algebra. This gives me an equivalence class of probability measure under the equivalence given by the fact that two probability measures have the same moments. So, for me, symmetric state will simply mean polynomially symmetric. Of course, we know that this doesn't mean there are well-known counterexamples to the symmetry, and polynomial symmetry is not sufficient to guarantee symmetry. Orthogonality is understood with respect to the measure mu, and as usual, the orthogonalization of the monomials will give the orthogonal polynomials, the sequence of orthogonal polynomials that I will denote by Pn. And this is the famous Jacobi three-dimensional relation in which you see the principal Jacobi series we denote omega n, and the secondary Jacobi sequence we denote by alpha n. It's very important that while the constraints between alpha n and the omega n and the connection is given by the famous Favart lemma or theorem, which states the following. Essentially, the idea is this. The sequence alpha n can be completely arbitrary, real numbers. The sequence omega n has two constraints. One is that the numbers are positive. And the other constraint, which is more subtle, is that if some omega k is equal to 0, then starting from that point, all the other ones are equal to 0. So, given the measure with moments of all orders, is the omega n and alpha n just come from the Gram-Schmidt orthogonalization. The essence of the Favart theorem is the converse statement, namely that if you give, I will formulate this more precisely. So, given that by orthogonalization, and you see this formulation we will call the monic Jacobi relation. Monic means that it's not symmetric. You see, Pn plus 1 and Pn minus 1 are not symmetric because it is understood that Pn plus 1 has the dominating coefficient of the degree n plus 1 is equal to 1. So here, this sequence, of course, we should specify that this is true for every n, assuming that omega n is different from 0 from every n, as you will see in a moment from the full statement of Favart theorem. Very important particular case is when the secondary Jacobi sequence is identically 0, and this characterizes the symmetric distributions. Moreover, the atomic distribution concentrated on a finite number of points are characterized by the fact that one omega k is 0. And we know by compatibility condition that then all other ones must be 0. The essence of the Favart lemma is the converse. The converse relation is that if I give two sequences which satisfy these above properties, then there exists one measure, probability measure, and one unique state on the polynomial algebra. Of course, not necessarily unique probability measure. For example, the famous Kahneman conditions are analytical conditions for uniqueness. So now let me give you a definition which apparently has nothing to do with this notion. This definition was motivated by very complex application of the stochastic limit to quantum electrodynamics. I have no time to go into the detail, but we found some very complicated formula, and in order to give a meaning to this formula, we introduced an axiomatic definition of a generalization of what is known as the Fock space. Mathematically, this generalization is very simple. I just tell you the essence. What is the essence of interacting Fock space? Interacting Fock space is the most general Hilbert space, which has a gradation, that is a decomposed in a countable direct sum of orthogonal subspace, and with respect to this gradation, it is possible to define a creation operator and an annihilation operator. So the essence of interacting Fock space is this. This seems to be very abstract, very general, but in a moment you will see that this structure is rather rigid. And the rigidity, at the end of my talk, will bring us back to the condition that we found in the Favart lemma, that if one omega k is equal to 0, then all the other one are equal to 0. We will see that this condition in the multidimensional case becomes the necessary condition for the fact that the creation operator is well defined. But this will come at the end. So, what is interacting for space? We take either the full tensor product or the symmetric tensor product. The full tensor product was originally the one that we found because for some strange reason in quantum electrodynamics, without dipole approximation, the diagrams that come out are not the Gaussian diagrams, but they are the free diagrams, the non-crossing partitions. This was something surprising, but it is so. So that is why we have to need both. This is to cover the quantum electrodynamics without dipole approximation, and this is the more standard situation in which you have boson case. So the zero power is just 0 by definition, and then we have, the important point is the following. If you take an arbitrary vector space and you do either the full tensor power or the symmetric tensor power, you can always algebraically define such operator, which is called the creation operator of, or symmetric creation if you take symmetric tensor product. However, if you put a scalar product or a pre-scalar product on this tensor power, and you want that this operator is an adjoint, then some constraints appear. And in a moment I will tell you the precise constraint, what it is. So, the definition of the precise definition, I gave you the idea, but you see that the definition reflects the idea. We say that we have an interacting Fock structure on a vector space if we have a sequence of scalar product. So this is the important distinctive from the usual Fock space. In the Fock space, in some sense, the scalar product are all the same because they are all the tensor product of the one-dimensional scalar product. But here, we can give almost completely arbitrarily the scalar product on each n-particle space, which is the nth tensor product. So we start with the zero tensor product, which is a one-dimensional space defined by the multiples of a single vector called vacuum. And important point is that we require the existence of we require the fact that with respect to each scalar product, so for each n, the creation operator, which remember was defined before, is an adjoint. Creation is simply the tensor multiplication or the symmetric tensor multiplication by a single vector. So, if you take this is in the space of n minus 1 particle, and you add one particle in the physical intuition. Okay? And the idea is that this operator is an adjoint. So, since the creation brings from the n minus 1 particle to the n particle space, the annihilation will bring from the n particle space to the n minus 1. Okay? So you see, the constraint that I was mentioning before is very simple. If I go from if I start from a vector n minus 1 and I form this tensor product, if this vector has a norm 0 in the n minus 1 scalar product, Of course, a necessary condition is that its image is 0, and therefore it must have norm 0 also in the n scalar product. It's a very, very, very simple condition. So this, in fact, you see that this condition reminds very much the condition in the Favart lemma. And in fact, we will see that this is exactly the multidimensional analog of this condition. All what I said is at the level of a pre-scalar product. For the orthogonal application to orthogonal polynomial, it will be very important to distinguish the algebraic level, which is pre-scalar product, from the analytical level, which is the quotient of the completion of the Hilbert space, which requires a quotient procedure. And therefore, the quotient procedure depends on the probability measure, which is the state. But the algebraic notion is purely algebraic and allows us to work on the polynomial algebra. So, this is the definition of interactive Fock space. The symbol, we use gamma because gamma is the usual symbol for boson Fock space over this one particle space V. But in our case, we give a sequence of pre-scalar product, then we complete the nth tensor power, and now we have a Hilbert space. And this is the definition of interactive Fock space. Since we have a gradation, we have a number operator which is simply defined as a self-adjoint operator which is identically, whose restriction on the n particle space, the nth term of the gradation, is identically equal to the natural number n. So, this is any gradation with the index set natural number is a number operator canonically associated. Okay. So let me now, to make the bridge with orthogonal polynomial, let us see how this abstract construction looks like when the simplest case in which the vector space V is one-dimensional. So it is isomorphic to the complex numbers. In this case, we have a one-dimensional pre-Hilbert space. And so the scalar product is uniquely determined by a positive number. By a positive number times the usual scalar product on the complex numbers. And therefore, the n-particle space is one-dimensional or zero-dimensional, because lambda n may be 0. Here is what I was saying about the quotient. Algebraically, the tensor power of C by itself is always C. But when I introduce the measure, I must keep count of the fact that I can have atomic measures. And in this case, the n-particle space from a certain n on is identically 0. Atomic concentrated on a finite number of points. And so we have this gradation. But now, remember, we had the compatibility condition for the lemma. What is the compatibility condition? Compatibility condition means that lambda n is 0, so the nth scalar product is 0, if and only if all the other ones are 0. This is the condition for the creator to exist. And you see that it's almost identical to the condition that appears in the Favart lemma. And now, what is the connection between the two things? Well, I will give you the very naive idea, and then we formulate it as a precise theorem. What is the naive idea? Look at the Jacobi relation. Here is the multiplication by x. And here I have three terms. But one is in the upper level of the gradation, one is in the same level as n, as Pn, and another is in one level below. So if you know something of quantum mechanics, you naturally are led to introduce some linear operators. These linear operators are well defined because the Pn is an orthonormal basis. So they are densely defined. Moreover, they leave the orthonormal basis up to multiples into itself, so they are densely defined on an invariant domain. Okay? So I will interpret this operator, which brings the nth orthogonal polynomial into the n plus 1, I will call creator. This one I will call the preservation operator. This is annihilation. And the one which leaves the gradation invariant, I will call... of course. This should be 0. Sorry. This is the preservation operator. It doesn't change the variation. It leaves the variation invariant. Yes. So, and this is a theorem we proved long ago with the Bozzeico. We proved the following, that what is the relation with orthogonal polynomial? If we take, remember, Cx is the polynomial algebra in one indeterminate. If we take a state on this algebra, and then we can form the orthogonal sequence of polynomial, and therefore we have the two Jacobi sequences. And now the connection between the lambda n of the interacting Fock space and the omega n of the Jacobi is simply that we have this generalized factorial that comes out. Or equivalently, you have this quotient relation, which has a meaning because both sequences satisfy the same constraint, that if one is 0, all the other one are 0. So this quotient is well defined if we put it 0 when the first is 0. Okay? And what is important is that the converse statement is true. So if I consider, I can define a unitary isomorphism between the interacting Fock space. Remember, we decided to call interacting Fock space is determined by a vector space and a sequence of scalar products. In our case, the vector space is one-dimensional, and therefore the sequence of scalar products is simply a sequence of positive numbers. This isomorphism brings the vacuum state into the identity function of the polynomial L2. Polynomial L2 means the closure of the polynomials inside the L2 space. Okay? And what is important, I see that this is the nth orthogonal polynomial, and the left-hand side has an important physical interpretation as the n-particle state, as a state which contains exactly n particles. What makes this isomorphism non-trivial is this relation. Because, of course, any two separable Hilbert spaces are isomorphic. But what makes this isomorphic canonical is the fact that the random variable, the multiplication operator by the random variable, is translated, is brought by this isomorphism into this canon. So this is the operator theoretical formulation of the Jacobi relation. You see, alpha n is given a meaning in terms of spectral theorem, because alpha n is a self-adjoint operator. So for any Borel function of alpha of a real variable, I can form alpha of n, the composite function. So this has a meaning, and in fact, you see, it's defined like this. It's a more simple language without using, because in this case, we don't need, we have a discrete spectral resolution, so it's very easy. Alpha n applied to the n particle vector, we have only up to normalization only one n-particle vector is simply a multiple given by the alpha n of the secondary Jacobi sequence. So this is what we call the quantum decomposition. You see, we have a random variable which has moments of any order, standard, completely classical, but this random variable has a kind of microscopic structure, and it can be expressed as a sum of creator, annihilator, and a function of number operator. And this is true for any random variable with all moments. We have a generalization recently for any infinitely divisible random variable. But we don't know if a random variable, which is either not a moment of any order or not infinitely divisible, we don't know if it exists such a kind of decomposition. This is a problem that I would like very much to see its solution done by anybody. And the converse is true. So we have seen that if we give the measure that is the orthogonal polynomials, we can go to the interacting Fock space. Conversely, if we give interacting Fock space, we use the Favard lemma to obtain the alpha n uniquely in terms of, in fact, we can say the following. The interacting Fock space is uniquely determined by the principal Jacobi sequence. And for arbitrary choice of the secondary Jacobi sequence, we define a random variable. Because you see, the important point is the principal Jacobi sequence. We will see in a moment that all in any equivalence class of probability measures on the real line, for the equivalence relation of having the same principal Jacobi sequence omega n. You can have infinitely many measures, of course, because the alpha n is totally arbitrary. But all these measures, which have the same principal Jacobi sequence, they define the same interacting Fock space. And this I will show you in a moment. Now you understand what is this commutator. This commutator is A times A daga plus minus A daga A. But A daga brings n, the space Hn into Hn plus 1. A brings Hn plus 1 into Hn, so it means that both A daga A and A daga preserve the gradation. But if they preserve the gradation, of course the gradation is made by one-dimensional spaces. These operators on each space of the gradation is a multiplication by a number. And the simple calculation shows that this is the form of the commutation relations. So now we have proved that the commutation relation don't come from quantum mechanics, they come from probability theory. Because every probability measure which has moments of any order is canonically associated to the following commutation relation. These are a strong generalization of the Heisenberg commutation relation, but let us look what happens. If you take the most famous probability measure, you know the Gaussian, you know that the principal Jacobi sequence of the Gaussian is the integer, and so the canonical probabilistic commutation relation, you see, the n operators disappear. You have one, and you find the Heisenberg commutation relation. But you know that, as I said before, the commutation relation of the Hilbert space are uniquely determined by the principal Jacobi sequence. And you know that the Gauss and the Poisson have the same principal Jacobi sequence. They only differ because the secondary Jacobi sequence is non-trivial for Poisson. So it means that the Gauss interacting for space and Poisson are the same. And this fact was empirically rediscovered by many, many authors during decades for the Fock corresponding Fock spaces. But there was no theoretical principle. And this explains very clearly that it is a very general phenomenon. Any two probability measures with the same principal Jacobi sequence will give the same interacting Fock space. Okay. And now let us go to the more difficult part, which is the multidimensional generalization. It took about 15 years to go from the one-dimensional case to the multidimensional case. And it took many, many steps. I will not have time to reconstruct them historically, but I want to give you the main idea of why this, what is the generalization. So, just for notation, now instead of one variable, we will take d variable. So we take a probability measure on Rd. And we fix the coordinates on Rd, and we call them xj. And of course, the obvious assumption is that all moments exist. Now we are speaking, of course, of mixed moments. This is the natural filtration. The filtration is done by the filtration associated to the degree of the polynomial. And this union is a union in algebraic sense. It means any, of course, it means any polynomial belongs to some, because any polynomial has a maximum degree. And this is very important. This is the first decomposition. It's not, we are at a purely algebraic level. We are not putting probability measures yet. We are not putting a state on the polynomial algebra. So this decomposition is simply a vector space direct sum. I put a sum with a dot to distinguish a vector space direct sum and Hilbert space orthogonal sum. Okay? So this is a standard decomposition in monomial, multiples of monomial. In fact, not really multiple, because here you have many monomials of degree of the same n degree, all the homogeneous monomial of degree n. They are a basis of degree k, they are a basis of the space that we denote P0k. And now we want to, I always implicitly give for granted that there is a one-to-one correspondence between states on polynomial algebras and probability measures on Rd, but in fact, it is not completely so. A state on the polynomial algebra, of course, induces a scalar product in the standard way. Any state induces a scalar product by taking expectation of A star B. If you have an algebra, you take expectation of A star B, this is a pre-scalar product. And you can ask, is every pre-scalar product on the polynomial algebra induced by a probability measure, at least one probability measure on Rd? And the answer is yes, but if and only if the coordinates are all symmetric operators with respect to the scalar product. So from now on, we will only consider scalar products for which multiplication by coordinates is a symmetric operator, and therefore we can say that there is a one-to-one correspondence between states on the algebra and scalar products. Okay? Now let me formulate the multidimensional analog of the Favart lemma. You see, remember, in Favart lemma, we have two sequences. One is a positive numbers, and another one is arbitrary real numbers. The analog is this. If you give a state, I call it, say, probability measure, but this is up to equivalent, polynomial equivalence. So, if you, moment equivalence, I would say. If you have a state on the polynomial algebra, we call it phi, then I have two sequences. But now, omega n is a positive definite matrix, positive semi-definite matrix. And alpha n is a map from vectors to Hermitian matrices. In the one-dimensional case, there is equivalence between maps and a single Hermitian matrix of dimension 1. So, omega n is a linear operator on the symmetric tensor product of order n. So you see, symmetric is not put by hands. It is canonical. Symmetric, of course, when I speak of symmetric and positive definite, I am referring now to this is the n scalar product of the interacting Fock space. And this is the standard tensor product of the Euclidean scalar product in the d-dimensional spaces. I have n copies of the d-dimensional space, and I take the tensor product with the tensor product of the scalar products on each space. So this is a density with respect to the Euclidean tensor product, omega n. And now we have the analog of the Favart condition. The analog, you can guess, is the natural multidimensional generalization of the one-dimensional case that you already have seen. So the idea is, I have this vector which has the norm induced by the omega n scalar product. And this vector has the norm induced by the omega n minus 1 scalar product. The necessary condition, you see, is much more subtle because it doesn't require omega n minus 1 may not be identically 0, may only have some degeneracy. Why? And this, this is not a theorem because we have not yet proved. My conjecture is that if omega n has rank k from 1n, then the measure is supported in a manifold of dimension k. For example, a measure on the plane with support on the unit circle. Of course, we can have such objects. And everything must be written in this generalization, in these matrices. Okay? So, what is alpha n? Alpha n is a sequence of linear maps from the d-dimensional space to the linear adjointable operators, which is on the tensor product, symmetric tensor product. These are finite dimensional spaces. So there is no problem with the definition of tensor product. And the important point is that the analog of the fact that alpha n is real in the standard Favart lemma is that the alpha n is symmetric for the omega n scalar product. And this is important. It's not symmetric for the Euclidean scalar product. And from this identity, you see, I'm always speaking of pre-Hilbert space. I don't want to take the quotient for a reason that you will see when I give you, if I have time enough, the idea of the proof. Because I want to stay as far as possible at a purely algebraic level without introducing things that depend on the measure, on the probability measure. So this shows that if you have zero norm, the alpha n automatically respects the quotient, the zero norm vector. Zero norm vector is mapped into a zero norm vector. And so, once you have this, essentially, what we have proved that every polynomial, well, here is a rather delicate point. I will come on it later. Let me just state the theorem and then I explain why it is so. Essentially, the orthogonal polynomial of degree k, the space of orthogonal polynomial of degree k is isomorphic to the symmetric tensor product. And you will see in a moment why. This is a very delicate point. Why is symmetric tensor product and not usual tensor product? And the scalar product of the polynomial induces the scalar product on the interacting Fock space. And as in the one-dimensional case, once you have the isomorphism, algebraic isomorphism between these two vector spaces, we have a scalar product on this tensor power, of course we can use the isomorphism to define a scalar product on this tensor power. Then we have to impose the condition that all the coordinates are symmetric for this scalar product, and then we get a probability measure on the multivariable polynomial. And so, also in this case, we have a gradation, and since these are finite dimensional vector spaces, and the scalar product is given by a positive definite matrix, which is the density with respect to the standard Euclidean scalar product. Now, we will see in a moment how to define creation and annihilation operators. It's it's a kind of intrinsic formulation of the multidimensional Jacobi relation. And again, we can speak of the orthogonal projection because now we have the scalar product. So there is a subtle point here. We had to develop a simple algebraic theory in which you can speak of projections also when you have pre-Hilbert spaces. But this is not very difficult to do. Okay, so we have the number operator associated to the gradation. Now the gradation is very complicated because it's the gradation of orthogonal polynomial. At algebraic level, we have a fixed dimension. But after the quotient, the dimension can be very different depending on the measure. And so, as usual, we can use the spectral theorem to define for a given map. You see, this is V is an element in the d-dimensional complex space. And I say that for every n, the secondary Jacobi sequence is a sequence of Hermitian matrices associated to this. This is Hermitian if V is real coefficients, of course. Then you extend canonically to complex coordinates, okay? And so we have this pair of sequences, omega n, alpha n. And like in the Favart theorem, we have the converse. If we have the sequence of omega n, alpha n that satisfies the compatibility condition that I have shown, then you have, of course, the interacting Fock space defined by the omega n, and you use alpha n to define the coordinate of a random variable. I want to emphasize that this is not completely trivial. Why? because we are not doing any assumption on alpha n or omega n, but the coordinates, if they are coordinates in the sense of classical probability, as operators are commutative operators. Okay? So we have to have this commutativity, which in this context is not a priori clear why it happens. And if we have a very quick glance, how much I have? Huh? 10. So just a very quick glance at the proof, what we do, just to point out where are the essential points. You see, once you have a scalar, remember, you have a prescalar product in which the coordinates are symmetric operators. So we know that it comes from a probability, at least one probability measure. Therefore, the orthogonal projection at pre-Hilbert space level is well defined. Once we have, since this is an increasing filtration by the degrees, the projections are increasing. So we can define their difference. Their difference is what is the projection on the n polynomial or orthogonal polynomial of degree n. And now what is the intrinsic formulation of the Jacobi relation? Very simple. Since the sum of the Pn are now mutually orthogonal by construction, and their sum is the identity. Therefore, I can always write this xj multiplied by Pn is written as a three-diagonal sum, which generalizes, but this is not exactly the generalization of the Jacobi relation, because this is what we call symmetric Jacobi relation. It's not yet monic. The Pn plus 1, you see here, Pn plus 1 and Pn minus 1 are treated symmetrically. The monic Jacobi relation is when we fix out the this is a little bit more general because it allows us to deal with the possibility in which the sum of the omega n becomes identically zero. Okay? So you see now, what are these? Remember, we are xj I consider as a multiplication operator. Pn projects onto the subspace of orthogonal polynomial of degree n. So this projects onto degree n plus 1, so you recognize that this is the intuitive analog of creator, because it takes something from Pn and brings to Pn plus 1. This is the preservation operator, because it takes Pn and leaves in Pn, and this is annihilation, because it takes Pn and brings in Pn minus 1. So we will define the creation, but now these are finite dimensional, because the orthogonal polynomial of degree n are the dimension is well known. Pay attention, I am speaking at algebraic level. The dimension of the, after quotienting, it depends on the measure. But I am speaking at an algebraic level, and we will see in a moment what is this dimension. So I define creator. This is, you see, what is the point? In a different language, not in the quantum probabilistic language, but these are rectangular matrices, except the preservation one. Because let us call mn the dimension of Pn. This will go from mn to mn plus 1, so this is a rectangular matrix. And this was the problem that caused so much delay in the solution of the problem. Because it's very difficult to classify rectangular matrices. We wanted square matrices, because the analog of the positive numbers are positive definite matrices. But we cannot define the notion of positive definite for rectangular. Okay? So that is why we wanted, and this, how we of course, now we define, on each finite dimension, we have defined the restriction of the annihilation operator on the n particle space, which is finite dimensional. So it is a matrix, it's surely well defined, and now we extend it by taking orthogonal sum. And this is densely defined, we know, and the space is left invariant because of the multidimensional Jacobi relation. So we define it on an invariant subspace. Again, we have now the quantum decomposition of any coordinate. Again, but now, you see, now it is what I think is a very interesting point of this construction, that we deduce non-commutativity from commutativity. Because we know that the xj are coordinates. So if we take them as a multiplication operator, obviously they commute. And let us see what this implies on the creation and annihilation operators. You see, we know that the coordinates must commute, and we know that they have a quantum decomposition. So, simply by using the bilinearity of the commutator, we have that a big sum must be 0. But pay attention of this sum. These are operators that change the gradation. For example, the commutator Idaga takes a vector in the element n of the gradation, homogeneous element of degree n, and brings to an homogeneous element of degree n plus 2. No other operator has this property. Since the spaces at different n are orthogonal, from this big sum must be 0, we can separate the homogeneous terms. And these are the commutation relations. For example, we get something that the physicists know very well in the particular case of the standard boson-Fock space, namely that the annihilators must commute. And obviously, taking a joint, you get the commutativity, the creator, and taking a joint, you get commutativity of annihilator. But now for every measure. And then you have this property. You see, this property has a meaning only for asymmetric measure. For the Gaussian, we will not have this, because A0, in a moment I will show that but this is well known in the theory of orthogonal polynomial, that A0, the secondary Jacobi sequence is 0 if and only if the measure is polynomially symmetric. So, but we have this non-trivial commutation relation with the creator and the preservator. And this is most important, we have some commutation relation between creator and annihilator. But now, the situation is complicated. You will see now in a moment how can we extract information from these commutations. Very many analytical properties of the measure follow, and structural property follow from these commutators. Okay? So we have some commutation relation. The fundamental point is that now we know that they are canonically associated to the probability measure. So this is what I mean. That, of course, when you have a measure that up to a linear transformation can be reduced to a product measure, things enormously simplify. And this is the case of the Gaussian. Okay? But now we can deal with more complicated cases. What I will use, and this, if you remember, I said why symmetric tensor product appear, and the reason why symmetric tensor product appear lies exactly in the fact that the creator commute. In fact, you see, if we consider the monomial gradation in the polynomial algebra, so without any scalar product, just because the coordinate commute, we have a very well-known fact in algebra that the space generated by the monomial of degree n is isomorphic to the symmetric tensor product. And this is why it comes symmetric tensor product with polynomials. But we want to have the symmetric tensor product isomorphic to orthogonal polynomials. And this is, of course, these are monomials, usually are not orthogonal for non-trivial measures. So, here we extract some information. We know that once we give the measure, we can speak of orthogonality. And orthogonality means that we can separate in the filtration of the given by the degree of the polynomial, the highest order part, which is orthogonal, but this is measure dependent, to the lower order part. So from this, you see, if you think of the Graham-Schmidt orthogonalization, you subtract the orthogonal complement on the projection, you subtract from a monomial its orthogonal complement on the n-1 degree. So the monomial will remain a single monomial with the highest degree. This gives the analog of the multidimensional analog of monic polynomial. So a multidimensional monic polynomial will be a polynomial of many variables in which the highest order term is done by a single homogeneous monomial. Of course, there are many bases which are not monic. I can do many bases in which the highest order term includes many monomials of homogeneous degree n. But these are very special bases because they are obtained by orthogonalization, Graham-Schmidt. And now, okay, this is the last thing I want to show you. Well, this is the symmetry that I mean. Now, once we have the commutativity of the creators, we can extend the map that we did with the xj, which are commutative variables, we can extend it to the n particle. What is the difference? Is that the n particle is now orthogonal. Is the gradation, which is done of mutually orthogonal subspace. And the monomial gradation is not orthogonal. Okay? So this is why there appears this isomorphism for every n of symmetric tensor product. Just to conclude, let me okay, the converse construction is obvious. We have already commented on this, I will not repeat. This is the converse construction, that if you have the pair, omega n and Pn, you transport the product using this isomorphism between Pn and symmetric tensor product. In this transport, why this transport is very delicate to be done, and it took so many years to find the construction? Because you have to do a very subtle induction construction. Remember, once you have the omega n and alpha n, you have to construct the commuting coordinates. And fortunately, you know that you are working in the polynomial algebra, in which the multiplication of coordinates is commutative. So the idea of the induction relation is this. One proves that when n is equal to 0, the annihilator is 0, because annihilator kills the vacuum. So when alpha 0 n maps the n into itself, and you have the multiplication by coordinates, because it's purely algebraic. It doesn't depend on the measure. So you have only to define, for if you have defined all the preceding n, for all the preceding n, the preservation and the annihilation and the creation, you only have to define the creation on the nth level. And that is what allows to go to the induction. Well, let me finished with an application to classical probability. This is a quantum characterization of the Gaussian measure. So the Gaussian measure now in n dimension is the only probability measure which is symmetric, so the preservations are all 0, and the commutation relation are what we know from Heisenberg, multidimensional Heisenberg commutation relation. So the Heisenberg relation deduced from orthogonal polynomials in the one-dimensional case exactly can be done in the multidimensional case. So you see, if in 800 some mathematician, expert of orthogonal polynomial, would decide to develop the general, because what we have used here is just algebra. Everything was known. A little bit the language of operator theory was probably not known in the 19th century, but all the elements were there to show that the commutation relations are in fact a manifestation of classical probability. That is why I say that quantum probability is not a generalization of quantum probability, but simply of classical probability, but simply a prolongation of it. Because the quantum decomposition of the classical random variable is canonical, is there, is not put by hand. We simply deduce it. Okay, I stop here, but if there are questions, I will answer. Thank you.
Okay, so my question is about the symmetry, in fact. So we see that we deal with the polynomial in D and determinate, and then the commutativity between this indeterminate, and use the symmetry in the interacting Fock space.
No, the symmetry is not commutativity. It's the fact that the preservation, the secondary Jacobi sequence, the generalized secondary Jacobi sequence is identically zero.
Yeah.
The alpha n sequence, the generalized, the matrix alpha n must be identically zero.
Yeah, when we wanted to construct the unitary isomorphism between the L2 space for the polynomial and the tensor product, symmetric tensor product on CD.
Yeah, they don't play role.
No role.
No, because as in the one-dimensional case, the scalar product is uniquely determined by the principal Jacobi sequence, which is the capital omega n, which generalizes the small omega n in one dimension.
Yeah,
so
because
the theorem is true for the same Hilbert space, is true for all the equivalence class. You can change arbitrarily the alpha n sequence. That is why it's called secondary, because it's much less important.
So if in this case, if we suppose that indeterminate for polynomial are non-commutative, if we start with this hypothesis.
You can have a symmetric measure with the non-commutative A and A dagger. A plus and A plus J may not commute with A plus A minus K. It will commute with A plus K, because all creators commute.
But
this is the general result.
Yeah, the commutative, the commutation between the creator. So, where the commutativity between I plus G and I plus K
comes.
yes.
Okay, I will explain the detail separately, but it's a simple point. Okay. I just show, I mean, intuitively it's clear. Because the A plus are the highest level, please.
Well, is it possible to introduce in such an approach some kind of unitary evolution, quantum parallelism, and analog of coherent states on Fock space?
Surely, there are.
And some graded sequence of Hamiltonians.
Yes. The coherent states in the one-dimensional case were introduced many years ago by Professor Das. And in multidimensional case, of course, they can be formally defined by the same formula. The problem will be the convergence. Our experience with the square is that while in the standard boson-Fock space, the coherent state have a radius of convergence which is infinite. Already with the square, you have a finite radius of convergence. So I expect that the problem of convergence will come out. So I say up to analytical condition on the omega n is possible to define. But we have to study the structure of omega n. Concerning evolution, sure, the alpha n is the analog of Hamiltonian. The alpha n is the analog, I would say, of the gauge evolution. Because we don't require that alpha n is positive, only that it is self-adjoint. But it is self-adjoint, it has an evolution. Since it's finite dimensional, on X and particle space, it gives a canonical evolution which leaves the n-particle space.
What is the time?
Yeah. Time is outside, like also in non-relativistic quantum mechanics is always outside.
And if this construction have some physical meaning, is it possible to perform some measures using your constructions and recommendation consequence as a consequence of this mathematical construction?
Yes, this is in some sense the origin of our construction, because the name interacting Fock space was chosen by us exactly to express this idea that, like the Fock space is very suitable to describe systems which are not interacting, because up to a linear transformation you get a product measure, and product means non-interaction. But we call it interacting Fock space because this complicated structure of this different scalar product is exactly the expression of interaction between the different degrees of freedom. For example, even in biology, we have some interesting proposal of biological interpretation, because there is these spaces are very suitable to describe interaction between species or between different types of particles.
Okay. There is a nice equivalence between the theory of orthogonal polynomials and the interacting Fock space. And to conclude, Luigi, please tell something in Russian.
Я надеюсь, что этот семинар сегодня, доклад, может помогать сотрудничество между нашей группой квантовой вероятности и люди, которые занимаются теорией ортогональных полиномиев.